Today our lecture will be solution of the high voltage network load regime with the help of modified Seudel method. First, I would like to show little demonstration. I have the demo. It's a rheostat powered from the mains. It has a driving. It's a driver and voltage. I have a load. 1, 2, 3. Common voltage of the load is taken to the load voltage is taken to the control system, and I have a setup set point for 150 volts. Control system changes position of the rheostat in the way what load should be 0. Drive it to 0. Maybe I can come a bit closer. Okay, it is my setup. You see measurements. It's a network voltage. I need yeah, 220. Load voltage and load power. Let's take a look what happens if I change load. Now load is 0. You can see control system change position of the rheostat. The voltage become 150. Now I have full load. You can see everything works. Control system return voltage to the set point. And now, why we are looking on the system? 1 second. I use this system to illustrate a connection of city distribution network. Let's say I have 110 or 115 kilovolt network, transformer, and 10, 11, 12 kilovolt. It's a distribution network. Should have used transformer and 0.4 kilovolt. It's our customer network. But our point of interest is this transformer. The moment this transformer is adjustable. At the start point is side here. At the neutral point there are connections which can be mechanical switched. So the transformer's radio becomes variable. So this this transformer's ratio can be changed to adapt to the load change of the network. It's done because at night it's a serious load decrease, and at morning rush hour and evening rush hour we'll see load surge. If we do nothing, at night there will be over voltage, and at that time, daytime, voltage will seriously decrease, possible even to make network unstable. So, here a special voltage transformer is installed, and signal at 100 volt is taken to the voltage controller. Voltage control sends change tape signal to transformer mechanic to tape's drive to adapt transformer's ratio in that way what voltage at the bus remain constant. We have, you can see my demo is somehow close to this voltage control installation. Voltage controller, simplest models keep constant voltage. More advanced model also account voltage drop in the network. So it's plus some scale factor, increase of current. What I would like to show, let me switch. Take a look how system reacts to the change of primary voltage. At this moment, 230 volts. I will shift down to something like 106, 148. Okay, 148. Take a look like this. 163. Look what's going with system. So, once more. I'll go back. Voltage 161. For control system, there is no difference. Voltage change due to load increase or primary voltage. You can see guidance system kept voltage, let's say not kept, but returned voltage to the set point, 150 volts. And look what its power, case load power. 35 division, it's should be multiplied by 2, so it's 70 watts. Take a look, I'm increased voltage to 230. Look what's going on. First we saw power increase, but control system places it back. Control system returns voltage to the normal, to the set point. The difference will, it will correct itself. But you see, power returned to the same level. I decrease voltage, power increases. Control system do what? Returning voltage. Yes, power increases. I increase voltage and power decreases. Control system returns voltage to its normal, to the set point. So at the first approach, we see load with the constant power. This is something quite different from classical electrotechnics theory. We see a moment when with the rise of voltage, current decreases because power is constant. How should we calculate a network? When we would like to find 100 kilovolts network regime, we will face problem because load nodes have the characteristics set by voltage control system, or characteristics defined if you want. What should we do? There are different ways. One of the possible solution is to, let's say, adopt classical methods with introduction of controllable elements. We can use controllable voltage source, we can use controllable resistance, but I personally prefer use of controlled current source being a function of voltage to reflect control characteristic. Let's assume simple model. Let's assume that generators also work with value constant. There are different control scenarios, maybe P2 constants, maybe Pu constants. We can reflect any of them. I just take this constant power, let's say, to make it more visible, just for simplicity. Let's define a power vector by nodes in that way that if generator is attached to the node, we will write with the plus sign, and if load is attached to the node, we will write its power, full power with the minus sign. If network topology is defined with the M matrix, so if branch in falls in node right -1, it falls from node right. We write 1, with no connection we write 0, and branch resistance lines and transformers resistance are in resistance matrix. Actually, we will fill only main one to number of nodes. We will fill only main diagonal. We should not take metal inductance in account for load regimes. We can start with nodal voltage equation. nodal admittance matrix multiplied by node voltage vectors should be equal to currents minus EMF vector plus base or slack node admittance matrix multiplied by base or slack bus voltage. Let's work with the current vector. We have a power vector of power by nodes. What can we write? We can define first, current of the load will be conjugated load power divided by square root of 3 and conjugated load voltage. Why? Actual power is voltage by conjugated power, current. But we have three-phase network, that's why vector of 3 should arrive. And one moment, traditionally, in such type of calculus, line-to-line voltage is used. That's why it should be square root from 3 to go to phase voltage. That's why load current is conjugated load power divided by square root from 3 and voltage. We can define D matrix being diagonal of conjugate divided by square root of 3. It's just for good notation. Can define this D matrix. It's diagonal matrix. If so, currents will be D here. This is one again conjugated voltage of the node I. Usually EMF vector is not incorporated. Well, you can use it, but usually it's not used, and we will see an equation. Nodal admittance matrix voltages is equals to plus, with this one it's very simple, equals to sum to number of nodes for each E from 1 to number of nodes. It's a admittance between node I and base node. It's simple. But what should we do with the system? Problem. But at this moment, we no longer have a linear equation system of classic electrotechnics theory. This system cannot be solved analytically So, what to do later on? We can use as an iterative or sequential method. Let's try to adapt classical Seudel method to this problem. Seudel method of solution equals of linear system solution asks us first to look to the Jacobi form where x next is found as the previous plus some vectors where are zeros excluding I equals R means I and is divided by R. It's a Jacobi form. We later apply the techniques to solve it. Jacobi iterative form. What will we do? This part remains as it is, but is a function of voltage. We can modify classic Seudel technique, keeping in mind what three elements vector is a function of voltage. What it will be. So should be minus divided by I for each I, no 1 to the number of nodes and for number of nodes. I are zeros, but it's not important. I'll show how. Now let's see how iterative function will look like. So voltage at the node I next will be sum from 1 to I. Next one. This part is a classical electrotechnic theory. Plus sum is 1. I should avoid multiplying by 0, it's useless. To the number of nodes previous plus 1 divided by I, but here should be I divided by voltage, the I nodes conjugated and previous plus I should change from 1 to number of nodes. get the idea. I can use fact what I have two voltage next one and previous, and use previous one to calculate current for the next step. 1 second, be right back. back. Oh, here I am. Sorry for interruption. So, what we got here is a modified Seudel technique. These two elements, are from classic Seudel technique, and this one we recalculate currents at every step for each voltage, estimation of each voltage, using previous voltage from previous step to calculate, to find current as a function of voltage. It's the simplest way. You can use any characteristic, just put it here. This should be current as a function of previous step voltage. Solution will yield us nodal voltage. Precision can be estimated as a maximum absolute difference, no problem. You see, in reality, what convergence is not so strong as in classic electrotechnics theory. Convergence is depending on first initial voltage. If you don't know some trusted regime, just use a vector of base or slug bus, base node or slug bus voltages. No problem. But convergence is dependent on network load. When network is near of its transfer capacity, method will converge with problem. But let's assume it's converged. You got voltages later. What branch current vectors? It's easy. E plus M transpose voltage and this bars base node voltage. Don't forget base node voltage. Usually we don't need currents or node voltage. In reality we need power flows. Power transferred by branch. So for its I will use Latvian ZAR, branch, vector of branch flow is formed in this way. So power flow in the branch number equals to square root from 3 nodal voltage at node I multiplied by branch current conjugated if not 0 from I starting from 1 to number of nodes and if from 1 to number of branches. Square root because we have line voltage and free phase. If you need losses, branch losses are resistance multiplied by branch current and multiplied by conjugated branch current from 1 to number of branches. Easy. So key moment is a usage of previous step voltage to estimate defined current for the next step. Let me show now. I have a program example in MATLAB. 1 second, I'll open it. Here it is, my small example. I have a simple network from 6 lines. Each 110 kilowatt network. I have assumed equal resistance for lines. It's for simplicity. So, yeah, resistance line length multiplied by resistance of 1 kilometer. It's just for simplicity. Here I have connection matrix. First incidence matrix. Measurements. MS, it's from Latvian mezglu skaits, it's number of nodes. ZS, zaru skaits, number of branches. Load generation. And case vector of loads. I define square root from 3 just for, it gives a bit of speed up. It's a constant. Here, you can see I'm creating a D in form of vector. I don't want to store a branch of zeros. Also, inversion of resistance matrix, since I don't have any metal inductance, I have direct sequence here. I can work with main diagonal only. Anyway, I have created. It's an inverse resistance matrix. It's no longer needed. So human work set here. This row creates a first approximation for voltage as a vector field with base node voltages. This part, transpose of the matrix, I need a transposed first incidence matrix. Here, nodal admittance matrix. This cycle calculates base node admittance matrix as a sum of the nodal admittance matrix rows. I don't need to conduct it myself. Classical preparation for Seudel method, calculation of C matrix, precision. Now I will calculate, since I will calculate, if you take a look, yeah, here it is. I set base node 150 kilovolts. So I will calculate in kilovolts, maybe 5 digit after the comma is too much, because it's in kilovolts, maybe 3. Okay, 4. Till the 1/10 of the volt. N is a number of steps. Cycle to iterate nodes. And here is my sum. First sum for the, let's say, new voltage. Second sum for the old voltage. And take a look on this part. Base node admittance vector element plus, here it is, this one, take a look. Yeah, this one. The selected one will produce current, let's say current injection in the node. It will be positive for generation and negative for load as a function of previous step voltage. And I need to divide it by diagonal element of nodal admittance matrix as a classical Seudel approach. Precision, max selection for the precision. I need a maximum absolute difference. And here it is. I'm putting my voltage in place. Number of steps, voltages to show currents. I calculate currents with the Ohm law. I didn't use E vector, EMF vector, so it's not present. Power flow, very easy. I iterate through nodes, I iterate to branch. If branch is connected to node, here it is, I calculate the branch power. What will, let's say, wattmeter put into corresponding branch show. Put them on display. Losses, here, losses for each branch, and also I calculate total loss of the whole network. This small part, I calculate sum of all active part of all loss. I need an active overall active load to calculate a real efficiency. TLK from Latvian liederības coefficients, tikko liederības coefficients, overall efficiency of the network. This one is total overall efficiency of the network. So let's run and see what happened. I should switch. Yeah. Let's take a look from the beginning. Okay, here are voltages. Yeah, we see voltages. Next, branch currents. Voltages are in kilovolts, branch currents in kiloamps. Power flow by branch. Yeah, power flows. Power losses in branch. Total active and active loss. Load totally consumes 108 megawatts. So network is working with 97% efficiency. Quite efficient. Here, without problem, I have solved problem. One moment, one note. I mentioned it. This technique, efficiency. Let's say convergence, is strictly dependent. Well, it's okay, not strict, but quite dependent of the network load. The method is not, it's not very good for highly loaded networks. Anyway, if you see what modified Seudel converge slowly, you should understand what your network is on the brink of the stability. Very possible it will fail. Anyway, this technique is usable. Okay, where am I? Here. Maybe some questions? Questions, please, questions. Maybe I write the correct formula once more. Next voltage in the mode number I can define as a sum in my from 1 to O next plus sum from I plus 1 to number of nodes, or in mathematical sky it's the same as number of nodes. Previous plus 1 again divided by voltage from previous step but conjugated, and this should be done starting from 1 number of nodes until epsilon being maximum absolute difference between voltage is not, until we achieve a necessary precision. It's a way to solve non-linear nodal voltage equation system emerging when we start to look at load and generation as they are, which characteristics are defined by control system, regulation law, not by the, let's say, natural law of Ohm, as it is with classical electrotechnics theory. Okay, I think it's enough for today.